In this section, we're looking at section 13.3 and 13.4 together. Okay? This is going to be the last section before the test. We have today and tomorrow to go over this section. Now, next week, when you guys are here, we're going to do a lab. The lab will take a single period. It's a rather straightforward lab. And then we have a review period. Okay? So keep in mind that this is kind of a shorter test topic. So it'll probably be only like 35 points, my guess. You missed a double the other day, and today's a C day. So I'm trying to do as much as we can, but just the timing isn't working out. If you look at the problem sets online, I put problem sets through even further sections. But obviously, since this test is 13.1, 2, 3, and 4, you're only going to do those for the problem set that's due next week. All right? So in this section, we're going to continue with this concept of simple harmonic motion. We're going to look at things that oscillate or vibrate or move back and forth. But now we're specifically going to start looking at the properties of those waves, such as frequency, amplitude, period, these things that we've talked about, but how they affect the actual graph. And in addition to that, we're going to look at how these waves interact with one another. Okay, so that's the main idea of all these objectives here. I'm not going to read them all off to you. So let's start with a couple quick definitions. Okay? A couple quick definitions. I'm trying to, and I told the other class the same thing, and I do this as the year progresses. Earlier in the year, I pretty much wrote a lot of the definitions for you in your slides. I'm trying to kind of wean you off that a little bit because I find that some people, if they have everything, don't really write stuff down and don't always focus. So for this, let's go through what some of these things mean first. So a wave can be thought of, and if you think about a wave like in a baseball stadium, have you ever been to a baseball game and everybody gets up and does this and the wave carries around? A wave is a disturbance. That's what it really is. It's a disturbance. It's a disturbance that's created by some sort of what's the word I want to use? The word is perturbation, but I'm thinking of a smaller word for that. A wave is a disturbance created by some input. Let's put it that way. A disturbance created by an input. So earlier in the last lab, we had the springs and the pendulum. Well, when the pendulum was going back and forth, it was moving in simple harmonic motion, which can be modeled by waves. But the pendulum itself was really, you pulling it up was the disturbance. Okay, you let it go, and then it continues to go back and forth. The wave itself, the vibrations are a disturbance. If you've ever, this is something that's real, by the way. Have you ever had phantom vibrations? You know, anyone ever researched that term? You'll know what it is once I tell you. All right, so have you ever been like maybe somewhere, I don't know, you're out somewhere where like you're in a place where you can't hear a lot because it's loud for some reason. And you keep thinking your phone is vibrating, but it's not. It's actually like a thing now because everybody carries their phones all the time. It's called phantom vibrations, where you feel like there's something vibrating your leg as if your phone is there, and you take it out and you're like, it's not going off. And it's happened to me several times. That's an idea of a wave. A vibration, your phone vibrating, is disturbing the molecules around it. That's what's physically happening. A phantom vibration, that idea is that like your mind that kind of tricks yourself because the air around you may be vibrating and it causes your leg itself and the skin and the actual like the material on your leg to oscillate a little bit, and you interpret that as a vibration of your phone. But a wave is like a vibration, okay, a disturbance. The word medium can mean many things, first of all. We're not talking about low, medium, high here. We're not talking about levels of difficulties in medium. But in this case, medium, we're thinking about, and the easy way to interpret this and remember, how many of you have ever seen, I don't know if it's a show anymore, but there used to be these shows where somebody like talked to this spirits in another world. They're called a medium. You know what I'm talking about right now? So somebody that could talk to like, your ancestors, they're considered a medium. And in that case, they're like a go-between, right? You speak to them and they speak to the spirits and then they relate it back to you. So it's the thing that your message is traveling through. That's what this is. The medium is the thing that the wave is traveling through. It's the material. The material that the wave travels through. So if you think about sonar, for those who have been on boats before who know anything about boats, sonar, what's the medium for sonar? For sonar waves. Anyone know, first of all, what are sonar waves and what would the medium be?
I think the medium will be water.
Yeah. Why is the medium water?
That's good.
You know it's water? Okay, what are sonar waves then? How about that part? What are sonar waves? Explain why is it water.
They bounce on an object and they bounce back to the thing.
Yeah, using what kind of waves specifically? Sonars. As sound waves. So sound waves travel different in different media. So air versus water, sound travels very different. And you know that. Have you ever been under the pool and tried to talk to somebody under the water? It's kind of weird, right, the way it sounds. I think it sounds distorted and stuff. Because the sound waves actually are traveling faster in the water than they do in air. So the medium itself can dictate, usually, not only the speed of the wave, but what can travel through it. For example, we're going to see in a minute here now mechanical waves. Mechanical waves require a deformable medium. A deformable medium. For example, let me use the example of two things so you know the difference. If you're on Earth, right, and you're talking to somebody, why are you able to hear what I'm saying? Anybody know how come you can physically hear what I'm saying right now? What am I doing to the air around me? I'm distorting it. Very good. I'm distorting it. Good way to use that word. I'm distorting it. I'm changing the air around me. When I speak, it vibrates the molecules in the air, which eventually get to your ear, cause your eardrum to vibrate, and then your brain interprets the actual pattern, you understand the language. Now, in this case, that's a mechanical wave that requires a deformable medium. An example would be sound. Although light does not require a deformable medium. And the easy way to recognize that is if you think about space. What is space? Meaning outside of the Earth, outer space. What does it consist of? What is the medium? It's kind of a trick question.
Where is it?
Good. It's nothing, really. It's a vacuum. Space is a vacuum. There is nothing out there. Literally. And I mean, obviously there's planets and stuff like that, right? But I mean, like when you're actually physically in outer space, there's nothing there. So if sound, as I told you, requires me to deform the molecules in the air so you can hear me, what happens if I scream in space?
No sound will come out.
No sound. Okay? No sound. It's kind of scary when you think about it. If you literally...
Can you like hear yourself?
So if you're in your little suit, it's totally different because inside the suit, oh bless you, there's a medium of air, right? So when you're in the suit itself, sure, you can talk. But obviously you would never not be in the suit, so it's kind of, you can't actually be there. But if you were actually in outer space and you like tried to yell, nothing would happen. You wouldn't hear anything.
That's where the saying comes from. In space, no one can hear you scream.
That's it, Jack. Very good. There's a saying that says that, and I agree. I love sayings personally. So that's a saying. That's where it comes from. That's the whole etymology behind that, because they can't hear you because there's no molecules to vibrate in space.
Does the sound depend on like whether someone like hears it or something like that? Because I was thinking about that question that's like if a tree falls.
In the woods, would you hear it fall, kind of thing? All right. So let's get out of philosophy and into physics for a second. If anything like makes a sound, sure, you may not hear it, but it does make a sound. Vibrations cause sound. So like even something as simple as that can be picked up by like sitting on a microphone. Now, in space though, because there's physically nothing to actually vibrate, nothing would be able to pick that up. You would never hear any sound because there's literally nothing vibrating. So a mechanical wave requires a deformable medium. Light, as you know, comes from where? Our light that we get on a daily basis. Where does it come from? Not this light. The sun. And the sun's rays travel through outer space. So light would not be considered a mechanical wave. It does not require a deformable medium. So the light can travel through empty space, and then it gets through our atmosphere. It gets refracted. We'll talk about refraction in about two sections. And it gets refracted, and what color do we see? Blue. The sky is not blue, actually, you know that, right? It's like the sky is blue? No, the sky's not blue. You're seeing white light that's been bent, refracted. We'll talk about that with refraction. But it's bent at a specific angle, a specific frequency, which provides blue light. That's why in a sunset you see all those colors, right? Because the sun is setting, it's altering the angle. A lot of the time it's also what's in the air that can change it as well. If you've ever been to like Alaska, and you've seen the northern lights, Aurora Borealis, I think it's called, the phrase, that comes from a magnetic field around the pole, and it tracks certain things, which change the colors. And all those colors, all comes from physics. The idea behind all those colors, where they're coming from. But you're not actually, like the sky is not physically blue. You understand that, right? There's no like somebody up there painting blue or anything like that. It's just you're seeing white light that's getting bent into the blue shape. So mechanical waves require a deformable medium. A pulse and a periodic wave. Let's talk about these now. Okay? Let's talk about these. So let's say this is a slinky is very easy to use to demonstrate a lot of stuff. So I'm going to use it probably like 4 or 5 times in this lesson. You want to grab the end of this? All right. So we have two terms here. We have pulse and we have periodic. If if you think back to our pendulum, because it moved in harmonic motion, we said it was periodic. We kept going back and forth, back and forth, back and forth, right? Now, what do you think the word pulse means? How do you think that differs from periodic? Where have you heard the word pulse before? If anybody's in video games, like a pulse gun is a word that's used, or in medical terms, or pulse measures something. What do you think pulse has to be? How does that differ from periodic? And I'm giving you a hint by saying it differs from periodic. Travis, what do you think?
Start,
Yeah, that's exactly it. It's like literally just starting it. Okay, now periodic would be me doing this. That's a periodic thing, where it's consistently happening. This is actually what's happening called a standing wave. Raise yours up a little bit. So this is actually called a standing wave. If I can get it down right, hold on. Try to keep yours still. I know it's weird, but try to hold your hand still. If I can get this right. At some point, you're going to see how the middle is oscillating up and down. You see that? There it goes. See the middle? Look at the middle. See how it's oscillating? And you go, point to it in the middle of these two waves. See where it's not? See right here? The height is not actually, it's hard for me to move to that. When you vibrate a wave, sometimes the wave could just oscillate up and down. It's called a standing wave. But the concept of periodic would be literally doing this over and over again. Whereas if Ben, let's put it down so it's not vibrating, right, lift it up. So if Ben, just go like this to me. Ben sends a pulse, the pulse gets returned. And we'll talk about the difference between a pulse that moves like that versus a pulse that moves like this. Okay, see the difference? One, it's moving what? So let's put it down so it dampens. All right, back up. So one pulse is sent in the direction the wave is going that way, and I'm going to push it that way. We're going to talk about this kind of wave in a minute. Whereas the next one, the wave's going to travel that way, but instead of pushing forward, I'm going to pull down. You see the difference in the wave? Okay, so we're going to use this a lot as an example to help us describe these things. But so you understand the idea of the difference here. A pulse is a single wave. A single wave. A periodic wave is a wave or set of waves generated by a source. By a source. Okay, so that source can be anything. That source was my hand a minute ago when I was going like this over and over and over again. In your lab, you're going to see an example of a periodic wave where the source is what's called a crankshaft, where it's just rotating over and over and over again cyclically. And I was going to show you that one. I'll show you tomorrow in class because we have a longer class. And I like to show a couple of demos on the computer so you can see simulations of these also. Okay, but again, the difference, pulse, single wave, periodic, it's generated over and over and over again by some source of waves. Yeah?
So a heartbeat, is that...
All right, heartbeat is many pulses, but technically it's periodic. The problem that it's not periodic is that periodic usually implies that it's the same wave over and over again. A heartbeat is not consistent. I mean, it is, but it's not, really. It's at a really precise level, it's definitely not. But usually you have a certain rate, the heart's beating at this rate. But what happens when you start writing? Beat goes up a little bit, then it goes down. So it's not really consistent, but theoretically it's got to be periodic for you to live. If it wasn't, it'd be a pulse, right? And then it would stop. I don't. It's impossible. That's where the word pulse comes from. I'm not really sure there. All right, so let's get to the two main types of waves. Let's try to at least get through that today. We have a bit of a shorter day, but I want to talk about these two. So this first example here. Okay, this was the example we just did. So this was the first example where we were looking at. So we're looking here at transverse. So we're going to talk about transverse and longitudinal. But specifically, let's look at transverse first. Transverse is the idea that the oscillation moves back and forth, but the vibration moves up and down. See the word perpendicular? Perpendicular, right? The y-axis and the x-axis, they are perpendicular. So when I send a single pulse, that pulse gets returned, keeps going back and forth. Now, when I send the pulse over to an ego, the wave is physically traveling left to right or right to left. It's traveling horizontally. But if you notice with my hand, what did I do? I went up. And the actual wave is going up and down. The particles are actually vibrating up and down. This is an example here of a source that creates a periodic wave. A blade, a vibrating blade is the example. If the blade continued to do this over and over again. Well, you saw when I did that with Ben a minute ago, when we kept doing this, the wave, it was oscillating up and down, right? But technically speaking, you kind of see the wave moving back and forth. So what's happening here is that the vibrations are up and down, while the wave travels left to right. So if you look at a point on the slinky at any point, that point of the slinky is just going to go up and down. So let's try and create that again. So I'm going to try and create a standing wave where if we continue to oscillate over and over again, I want you to look and find a spot on the wave that just goes up and down. Okay, and you'll see that it'll create like a little bit of a curve. So this will be, all right. See how in the middle it's really not moving? Can you see how this is really like two half waves? The side by knee goes going up and down, the side by knee is going up and down. The middle though, see the middle there? The middle is like stagnant, it's not moving. The term for that in physics is called a node. The middle is physically not changing position right now. Yet this is going up and down. So whether or not you realize it, the wave that we're sending, by going like this, the wave is going back and forth, but the actual material is going up and down. Okay, an example of this that you can really very easily see. You drop a pebble in a pond. Ever seen the ripple effect? When ripples move out from a source? Well, which way is the ripple affecting? It's moving laterally, right? Outward. But if you actually look at the water, what is the water doing? Isn't the water going up and down? The water's acting, like if you look at the ripple does this, right? It goes up and down, the water goes up and down, but the wave is propagating outward. That's a transverse wave because, again, the vibration is vertical, yet the motion of the wave is horizontal. When the vibration is up and down and the motion is horizontal, we call that a transverse wave. The easy way to remember this, the letter T, the lines are what? Perpendicular. Transverse, perpendicular. You see that? So simple mnemonic. Transverse, the letter T for transverse is perpendicular, those two lines, the letter T, it's perpendicular in the fashion. Because in a minute we're going to talk about parallel. Okay, so you're going to have to remember which is which. Longitudinal, we'll see, is parallel no longer. But for now, transverse means up and down. Up and down. Now, look at the bottom right figure. This is what we have to speak about for a little while. And I think you're somewhat familiar with some of these terms. You may have seen them in like an earlier science course. Maybe not in bio or chem, but maybe in like a physical science course or an 8th grade general science course you've used these words. So trough and crest are old words, really. They're not used as often anymore. What are words we might use now for the top of a wave and the bottom? What might the words be that you use? Good. Like a max and a minimum. Good. So the trough is a min, the crest is a max. That's all it is. Now, any wave that travels in this fashion where the amplitude is not changing, see the amplitude of the wave is the same throughout, is a wave that's continuously produced, that's in harmonic motion. Now, in reality, what do we know? What happens to like a pendulum, right? I release the pendulum. Does it do this forever? What does it eventually do? Right? It eventually stops at the bottom. So if you think back to the word amplitude from earlier in this section, in the last section, amplitude was how far we raised up the pendulum, or how far you pulled down on the spring and then let go to watch the spring oscillate. So amplitude was the deviation from the norm. So look at the graph. It makes complete sense now. The norm is the x-axis. The x-axis is like equilibrium in a sense. Well, how far does the wave travel away from the x-axis? This is the amplitude. So what's happening here versus here? This one, the second graph I just drew is an example of what's called damped harmonic motion. The first one that we're seeing up here, this is simply harmonic motion, where the wave continues over and over and over and over. It's called a sine wave. You're going to learn about it later this year and a lot more in pre-calc next year. But these are called sine or cosine waves, like the trig functions, sine and cosine. These are the graphs of those shapes. Okay, the fancy word is sinusoidal, but it's a sine wave is what it means. Okay, a sine wave or a cosine wave. Now, what's happening here is that we're able to measure the wavelength and the amplitude as our two parameters. And the wavelength has this weird looking symbol here. This symbol, I don't know if I've discussed it with you guys, is called lambda. It's pronounced Lambda. I don't know if it's spelled down. Phonetically, it's pronounced lambda. That's how you would say it. I think it's a Greek symbol. It's Greek or Latin. It's definitely Greek. I don't know Latin. And it pretty much tells you how long the wave is. How long is the wave? And if you remember, we talked about period. Period and wavelength are very similar to each other. The wavelength is physically how many meters long the wave is. The period is physically how much time it takes for one wavelength to cycle through. Again, a period is a measurement of time it takes For the pendulum, when we did the pendulum, if you recall, you raise the pendulum up and let go. One period was when it came back to where it started. So this was half, full period. Well, that time it takes to go through and back is on a graph shown as one wavelength. So this could be like the starting point up here. So start at one of the crests, go crest to crest or trough to trough to measure a wavelength. So if I think about this amplitude, starting amplitude right here as being up here. Now, follow me please. As I let go, it comes to, what is this called at the bottom again? What is it called? Minimum. Sure, that works, but what is it? Equilibrium. And then it passes through equilibrium and comes out the other side. Believe it or not, that's this right here. That's this portion of the graph. And then what happens? It goes from the other side, which is out here, negative side, passes back through equilibrium and back to where it started. So the time period that it takes for this to occur is analogous, in a sense, to the wavelength on a graph. Again, one wavelength in length is also equivalent to the time it takes for this wave to go from here back to here, or from here back to here. So for a lot of these, we want to consider, if we start at some given point, we need to end at that point. So if you want to consider here to here a wavelength, that's fine. I could also consider here to here as a wavelength. So I could start here, go to my extreme, pass through equilibrium, and come back. Or I could start up here, go through equilibrium, and come back. But what you're noticing here is that no matter where I measure, here to here, or here, I'll draw it with blue so you can see it, or from here to here, the value of lambda is the same for all of those cases. It's literally the length between these two parts. The length between these two parts. The length between these two parts. Okay, now, you can easily get confused with this because of the fact that wavelength and period are really both measurements of a full cycle. But one measures time, period measures time, and wavelength measures length. It's in the name, right? Length. It's in meters. What else? This cycle will continue indefinitely. Okay, this will go on forever. If it's harmonic motion, the graph will continue. This one at the bottom here, this one at the bottom is damped harmonic motion. It's the example if your car goes over a speed bump, what happens to it? What happens to your car after it goes over a speed bump? Does it continue to bounce up and down forever? Yeah, it does like one bounce and then it kind of like settles off. That's this graph right here at the bottom. Okay, it's called a damped system, All right, let's take this now. Let's go to the second type of wave. So the first type of wave that we just produced was transverse. The next one we're going to look at is going to be longitudinal, and this is really hard to explain, and it's hard to visualize. So a Slinky does a good job of it, and I'll give you an example in a minute that helps. So earlier we did this, right? Okay? The oscillations were which way? Up and down. Yet the waves still traveled left to right. So again, if I sent one pulse earlier, you can see that the waves still travel left to right, the oscillations were up and down. That was transverse. Now, the other type of wave that I think Ben did this earlier, when I said Ben used to do that, so do the same thing, just like send a pulse, yeah. So what he's doing now, let's do it one more time. And by sending a simple pulse like that, you're causing the molecules to oscillate this way. So this example here of a longitudinal wave is really where sound comes from. Sound is a longitudinal wave. When you speak, you cause the molecules in front of you to vibrate. I'm doing this to show you that if I put my hands here, you don't hear as much because those sound waves are not causing as many molecules to vibrate. It's not getting to you. It's diminishing by putting my hands here. I'm blocking the sound waves, right? So the sound waves cause all molecules to vibrate, and that's what's happening. If you've ever been waiting in line somewhere, a concert, a sports game, waiting for a new product to come out of the store, anywhere, I mean like a long line, all right? If you noticed, a line is a longitudinal wave. Okay, the bouncer, the doorman, or whoever it is, the place you're going, says, okay, we can let 10 people in. 10 people come in, right? What happens? All of a sudden, the next 10 people all move to the front, those next 10 move to there, those next 10 move to there, and isn't there like a gap in the line until it gets filled in? That's what a longitudinal wave is, physically. So a line that's waiting, where everybody's like, okay, I'm going to go, and then stop. Oh, then let 3 more people in. Go, and then stop. You're doing that over and over again. You're vibrating forward and back. That's an example of a longitudinal wave. Now, the tricky part of this comes about when we take a look here at this graph. This graph is showing that it still behaves like a sine wave, even though it's not molecules moving up and down anymore. But you're looking, instead of the vibrations, you're looking at the density of the spring. So if you look at this area, x1 over here, it correlates to x1 over here. What's happening, when I sent that wave, that pulse, where Inigo was holding it, I sent the pulse toward him, the spring compressed, and that compression moved. So this example, can we do one more time? This example is like 2 pulses. And that's going to be a little hard to do. We'll try it. So if I went like this, ready? So there's actually 2 pulses moving back and forth now. So I'm literally going 1, 2. Sending 2 pulses back. And what you'll notice is that some parts of the slinky will contract. And then they'll expand. That's what allows the wave to move back and forth. So if you look at the density of the coils, you'll see that the spring has some areas that are really dense and others that are stretched. Well, where it's really dense, you think of that as like a positive amplitude. Where it's really stretched out, you think of that as like a negative amplitude. Then that's a positive amplitude, then a negative. And in between that, you have a continuum of different stretches or compressions. So the idea here again, though, is that a longitudinal or a transverse waves both can be represented by a sine curve. Again, we're not going to go into a lot of details in this course, but in your math class, you're going to do a lot with sine and cosine waves. Let me think of anything else. One last example of longitudinal, that's a good one that people to get sometimes, is a pressure wave. And you see that with, like, if you've seen movies with explosions, when an explosion occurs, it sends out like usually some sort of a pulse, a pressure wave that causes people to get like thrown, literally. That pressure itself is also a longitudinal wave. It affects the layer of pressure in front of it. So the air, maybe the air pressure here is one value, then if something explodes, it causes pressure to come out of it like a gradient. So the pressure has different levels. Well, that pressure pushes this air, which pushes this air, which pushes this air. So the wave of pressure is traveling this way, and the air, God bless you, is also compressing this way. So when you see that the compression occurs left to right, and the wave is moving left to right, you can see that those things are parallel. And that's where this case comes into play. Okay, the word longitudinal, look at the word longitudinal. What does it start and end with? What does it start and end with? What letter? And 2 L's next to each other look like what? Parallel lines. Longitudinal has 2 L's in it. Remember, longitudinal has to do with parallel motion. Transverse, the letter T, looked like a perpendicular line, right? That had to do with perpendicular motion. So when it comes to remembering which is which here, it's an easy mnemonic device just to use the word itself. Okay, but again, these molecules, they're vibrating front and back, and the wave is moving front and back. Earlier, the molecules are vibrating up and down, and the wave is moving left to right. Another example of transverse, the last type of wave that I like to use because it's a little bit relatable for some students. If you've played any string instrument before, if you play guitar, why do you hold your hand at different locations on the guitar as you're playing? What does this do? Changing the location.
Makes the vibrations longer or shorter.
Yeah, it's changing the wavelength or the vibrations or the frequencies. So what's happening there when you pluck on a guitar string, you get a standing wave. The wave just oscillates up and down, up and down, up and down. But which way is it really traveling? The wave is traveling left to right. Okay, but the oscillations are up and down, and left to right together mean perpendicular. So when you pluck a guitar string, you're looking at a transverse wave. Okay, transverse. Anyone know times on a C day? 17? 17? That's close, man. 25 on an A day, I know as well. All right, so let's finish with this slide then. We've got about 2 minutes. Let's finish with this, and we'll pick up with this tomorrow. So, the speed of a wave could easily be derived using the simple formula for velocity earlier in the year. So let's start with that formula right here. So here's the formula for velocity from earlier in the year. V equals x over t. What did x stand for? Displacement. Like distance, it works. And t stood for? Okay. So if I'm thinking about distance, I'm thinking about a length. I'm thinking about a length. So the length of a wave is called the wavelength. So that goes in for distance or displacement here. The time it takes a wave to travel is called the period, right? So replace t with the period itself. So this is the formula that we end up with right here. And that's fine, and we could stop there. And that would relate period, wavelength, and velocity of the wave, or speed of the wave. Now, the other way to represent this is to replace period right here, replace this period with its equivalent expression, which is 1 over the frequency. Remember, period and frequency are reciprocals of each other from last section. You should know this by now after doing that homework. Period and frequency, and the lab. Period and frequency are reciprocals. So we can replace period with 1 over the frequency. What happens, though, when you divide by a fraction? What's the definition of division of a fraction? Division of a fraction means by the reciprocal. Multiplication by the reciprocal. So I can look at this situation and say, well, this is really the following. It's lambda, instead of divided by 1 over omega, times omega over 1. Again, instead of taking lambda, some number, and dividing it by a fraction, I'm going to multiply it by the reciprocal of that fraction. So this just becomes v equals lambda times omega. And that's the equation that we're going to use at the end over here. I'll zoom out so you can see this a little better. Okay? So again, this goes to here, which really is just simply this. So this is our equation that we're going to use. So the velocity or speed of a wave is the product of its wavelength and frequency. Good, guys. All right, so tonight you don't have homework, but if you want to, you can actually get a head start. Okay, if you want to get a head start, you can do that. And your problem set you can get a head start on, but we'll finish this off tomorrow. Don't forget office hours today. Okay, feel free to come by for office hours, please. Example. So, the first example has to do with a musical instrument. So for anyone that plays a musical instrument, you know that when you play a note, the note has a specific pitch. The pitch of the note indicates the frequency of the wavelengths, or the frequency of the waves, I should say. If you know the frequency, you also know the wavelength. So let's take a look at this example. So this is anybody, so raise your hand again if you play an instrument so I have an idea of people that have some knowledge of music. Only a few, okay. Well, do you know when you tune in the beginning of a concert, or if you ever want to tune your instrument, you use a concert B flat, and everybody has the same note, and you listen for the harmony of the note. Usually the piccolo or the oboe is the person, rather, that tunes everybody. So for a trumpet, you play a C or middle C, and that's a concert B flat. It's like your standard note. What I want you to recognize is look at the size of the wavelength. So it's kind of weird to think about this, because if I play an instrument, or if somebody plays a note on a certain instrument, you'll hear it. Now, the wavelength is 0.72 meters. That's this long, from the beginning to right here. So this is literally from here to here, the length of the wavelength from a musical instrument. So I don't want you to be having the mindset of, well, if I can hear it, it must be able to fit in my ear, so it's a small wave. That's like a common misconception about it. It makes sense though, right? It really does. And with like X-rays and gamma rays, the wavelengths are extremely small, like nanometers, which actually is part of the reason why those waves can affect your body on a molecular level. Gamma rays, any sort of radiation treatment for any sort of cancer patient would be wavelengths that are in very, very small orders. So they actually can affect your body on a molecular or atomic level because of the length of them. Now here, though, yes, the wavelength is like almost a meter, but you can still hear it. It doesn't have to fit in your ear. Okay, because I'm going to talk about gamma rays, and this is the misconception that people think, oh, it's such a large wavelength, how could you hear it? The speed of sound varies based on the medium. We talked about this last class. Sound is a function of the medium. Sonar, sound waves in water. Sonar is sound waves that are going underwater. Actually, sonar waves travel faster than sound waves in air. It has to do with the material itself, with the density of the material. Okay, water is a lot more dense than air. Waves that require a deformable medium, mechanical waves, as we spoke about yesterday, depend upon the density of the material that they're passing through. So when it passes through water, it travels at I think it's 1,100 meters per second for sound. Now we're going to see in a minute that light travels at an even different rate.
Wait, so like a plane travels faster than the radar waves, it won't pick up?
Technically, sure, but radar travels at the speed of light. Yeah. So radar doesn't use sound waves. Radar uses EM waves, which are electromagnetic, and all EM waves travel at the speed of light. So it's impossible to outrun a radar wave. Now, it's not impossible to distort the radar wave, which you've seen. Have you seen any of these new fighters? Yeah, they can actually bend using refractive surfaces the actual radar detector around it. These are things that are like undetectable. If you, I talk about this lesson, I don't a whole lesson on it, but I talk about this like when we get to EM stuff, but I'll give you a little preview. When, I'm terrible with history and names. Was it Osama bin Laden that was captured years ago? Or
And the one they killed.
was it Saddam? Who was more recent? Okay, somebody was more recent. And they actually landed, it was like a Navy SEAL operation, they like landed in the actual. Okay. So with that helicopter was insane. Have you heard about it? It's incredible. Not only did they make no noise, so this helicopter, like Mike said, completely generates no noise at all, or it's able to actually block sound waves from being heard outside of it. It does generate noise, but the areas around it can't hear it. It's undetectable by radar. The goggles that they're using are insane. The stuff that they have trained dogs that are actually wearing these same things. They can see through walls. It's absolutely incredible. The helicopter can jam all signals around it. So when they landed, there was no communication that was able to be sent out from the terrorist base. So it was really something nuts. But the idea here is that a lot of this stuff with frequency and wavelength can go a lot further than what we're going to do in this class. Okay, we're talking about simple stuff right now. Whether or not you believe me that it's simple, I mean simple on a big scheme, right? So really, all we're looking at here is we're saying, okay, here's the speed of sound, find the frequency or the pitch of the note. This maybe doesn't really help you, but where does this lead to, right? It leads to a lot more than just this. So let's start with our formula. V equals omega lambda in the previous slide. We know the speed of sound in air is 343 meters per second. We know that the wavelength, right, it says the length of a sound wave, that's the wavelength, is 0.72 meters. Plug and chug, right? Plug and chug. All you got to do is put your numbers in and solve for omega. If you want to plug in right away or solve for omega, if I were solving for omega, that's what it would look like. I would divide by lambda on both sides. Okay, if you're forgetting from yesterday again, this is lambda. This is called the wavelength. This is omega, called the frequency. And this is v for velocity, or in this case, speed. So our solution will just be v divided by lambda. 343 over 0.72. Now, if I think about units, my units of here are meters per second. My units here are meters. Right? Wavelength, length measured in meters right here. Velocity meters per second. Okay, so I get an answer, fine, but what are my units of that answer? What are my units? Meters definitely cancel, I'm done there. But what are the units going to become? Marilyn, what do you think? It's not seconds, close. It's close. It's not exactly seconds. Angie? Okay, it is hertz, but I want the breakdown of the units. What is a hertz, really? 1 over seconds. Because look, when the meters cancel, where is seconds, really? It's in the bottom, right? It's in the denominator, technically, the denominator of the numerator. So your units here could be misleading at times, because the units don't necessarily look like they match up. The units are 1 over seconds. But as we said a moment ago, that's defined as hertz. That's defined as hertz. What is the number we get? What do you get? 343 over 0.72? What is it?
476.4.
All right. Okay, 476.4 hertz. So what does that mean again? That means, ready? And this is kind of wild to think about. That means that when you produce this sound on your instrument, the vibrations occur at a rate of 476 vibrations every second. Every second, 476 vibrations. So again, we talked about this the other day with anatomy and with insects. Yeah, their frequency of vibrations is like 500. They can flap their wings 500 times per second. Again, a unit of cycles per second. Okay, and this is for sound waves. This is a little bit more reasonable, but for insects and stuff, it's kind of incredible to think about how much strength they must have in order to be able to do that. Okay? There was a commercial yesterday about I forget what the commercial was, but they were talking about like a bumblebee. I think it was either Honey Nut Cheerios or like a honey commercial. And like the amazing bumblebee can suspend itself. It doesn't make any sense, and it really doesn't. Have you ever seen a bumblebee before flying around? That thing looks fat. It looks huge. Bumblebees are like the big ones I'm talking about, not the ones that bite you, right? They're huge. And those wings are so thin and small, it physically makes no sense that they should be able to fly. But it has to do with how fast they're flapping their wings. Right? If I go like this, am I moving? I'm not floating in the air. But if I could do this really fast, I might be able to actually lift myself off the ground. And if I had like a bigger wingspan too. Right? I don't have enough contact surface area. But this is an idea of what you're looking at as far as rates, okay? This is cycles per second. 476 cycles every second. All right, let's go to the next one. So now we're going to go to the other extreme. We went from a really long wavelength of sound to now an electromagnetic wave, which we're going to get into in the next section after the next test. We're going to start EM waves. Well, in this case, to give you a little preview, an X-ray is considered one of our EM waves. An X-ray, obviously, you know, is used to detect for broken bones. When you get an X-ray, you go to the doctor, right? They look at the film afterward. You see white wherever your bones are. Wherever your bones aren't, you see like a navy blue, whatever the film color is behind it. What's happening there? Well, the X-rays themselves are passing through your body. Literally, through your body. But based on the material of your body, the bones versus everything else, the image looks different. Because the rays themselves are affected differently. So how many of you have seen, there's a movie called The Pursuit of Happiness with Will Smith. It was out years ago, but it's a pretty good movie, right? In the movie, he goes around selling, do you remember what he sells? Anybody remember what he sells in that movie? Oh, it looks like a little square, right? A little cube. Carrots are everywhere in the movie. He's got them all stacked up. They're bone, you know that?
They're done with bones, like checks the density of the bone.
It's a bone density scanner, very good. It was pretty much what was out before X-ray machines. This was a device that was used for a long time because it was pretty much like a portable X-ray machine, but it was extremely expensive to actually utilize. So when they have X-rays set up in like a lab, it doesn't really cost you much to do an X-ray nowadays. It's much cheaper than like an MRI. Very different. A lot less energy is used. But when he used to carry this thing around, that portable machine cost a lot of money. It was one of the first ones that was out.
So did he use like X-rays too?
Yeah, what the machine was doing, I don't know if it exactly used X-rays, but it used the density scanner, and because your bones are a different density than your skin, it was able to give you a picture of the bone. So you could like put a piece of your arm in there and it would scan what was in there. Now, with X-rays here, we're talking about really, really, really small waves. Really small waves. And if I have really small waves, I have to have really high frequency. And we'll see more of that in the next lab. You guys are going to do a lab when you get back from break, and you're going to see a lot more of that. But we'll see it here also. We can see it because of the relationship. So let's start with our formula. Now, if we look at this last statement, this is the most important part, right here. All EM waves travel at the speed of light. So Mike, this is part of your question about radar before. Radar is considered an EM wave. Any EM wave, colored light, UV rays, infrared rays, gamma radiation, radio waves, microwaves, not the devices themselves, but microwaves are called microwaves because they're on the order of 10 to the negative 6, micro. They use the speed of light as their constant for V here. So if I think about this, and the speed of light is always the same, 3 times 10 to the 8, okay? If I look at this, and I recognize that I have, so let's say I have a really high frequency. That means I must have a really low wavelength. Because the frequency and wavelength, good, are inversely related. It's not obvious because this is not one of those equations with a denominator, right? So this is one of the confusing ones. Usually when we see a denominator, we can see direct or indirect. Well, these two right here, please take a look what I'm pointing at. These two right here, these values are indirectly related when you're looking at EM waves because this is a constant. This is this number always, the speed of light. Think about it. The speed of sound we just did was 343. This, 3 times 10 to the 8. We're talking on the order of millions versus 343. So the speed of light is so much greater than the speed of sound. So much greater. That's why it's not really a feat anymore to break the sound barrier. It used to be. It used to be like, oh, you're traveling at Mach speed. Mach speed meant the speed of sound. Now there's Mach 1, Mach 2, Mach 3. You can break the speed of sound easily. And usually that creates a sound itself. It's called a sonic boom. How many Street Fighter fans do I have in the room? Anybody know Street Fighter? Remember Sonic Boom, Guile? Sonic Boom. Every time he would do that, he was creating a sound barrier, really changing the sound barrier. But what's happening here, I want you to recognize that if this is held constant and this number goes up, this number has to go down, and vice versa. So if you have a really long wavelength, so if this number is very high, this number would be very low. So I can tell already because look at the frequency here. Look at this frequency. 3 times 10 to the 12 megahertz. So not only is it a large number, but it's got the prefix mega there. Okay, it's got the prefix mega. And I purposely do that because I want to start talking about those prefixes. So, okay, we have the velocity of light. Yes, 3 times 10 to the 8. We got that there. We know the frequency is 3 times 10 to the 12 megahertz. Well, this is the point in the year where you have to start knowing our prefixes on the other end. So right now, you should know centi, milli, kilo. We've used those all year. We haven't used giga. We haven't really used mega. We're going to start using them. Okay, so that prefix table that we started on like day 2 of the entire year might come in handy. So if you want to remember your prefixes, mega is 10 to the 6, and giga is 10 to the 9. Kilo you know already, that's 10 to the 3rd. On the other end, you got centi, 10 to the negative 2. Milli, this is all on your sheet, so if you don't want to write it down, you have it already. You got micro, and you've got nano. Okay, these are the ones that, at this point in the year, you're going to end up using all of them. Micro, I mean, that's one you've seen already because you talk about things. I mean, in biology, you use the word micro all the time. Micro. Okay, what else? Even simpler. Yes, microscope. Yeah, microscope. A microscope was one of the first things to see things on the order of 10 to the negative 6 meters. It was very, 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 very small images, so it could zoom in really close. That's why that number is really small. Nano, you hear nanotechnology. Nano has to do with extremely small. Pico is 10 to the negative 12. So nanotechnology has to do with, you're looking at the material properties of something at that level. And that's a whole other lecture. I could spend 5 lectures on nanotechnology. But things change. The laws of physics change. Everything changes on the nanoscale. It's really kind of weird. Gravity is different. Resistance is different. Like we walk through air and we think this is easy, right? On the nano level, when particles are moving, the medium that they go through becomes like molasses. It's very different. Things behave very differently. So it's a little bit more depth than what we're going to go to, but just to give you an idea of where it's used. Now, so because this says mega as a prefix right here, we know that that's going to be 10 to the 6. So I have 10 to the 12 times 10 to the 6 is 10 to the... What do I do with exponents when I multiply things with the same bases? Add them. So 18. Again, this is what this really is. I replace the prefix mega right here with 10 to the 6. Replace mega with 10 to the 6. So as a result, my frequency that I'm going to use for this problem will be 3 times 10 to the 18. Okay, so I'm not going to use this line right here. That's just showing you the steps. I'm going to use those 2 numbers. Now, the math in this section is really easy. I'm not kidding. You can't do any more than just plug in the numbers at this point. So I'm not going to be asking you extensive stuff, but you need to know what? What do you need to know that some of you really struggled on the last test? What do you have to be able to use? Numbers in what form? What form are these numbers given in? More specific. Scientific notation. They're algebraic. Scientific notation. It's going to involve a lot of scientific notation. If you are having trouble with your calculator, you need to come see me after school or during a free, or at least advocate. Go to YouTube. Type in TI-83, how to use scientific notation. I will guarantee you there will be at least 25 videos. There'll probably be 100, but I can't guarantee that. But there will be at least 25, I'm telling you, on how to use scientific notation on a calculator. I would say out of 34 students in here on the last test, about 20 people ended up with a mistake on the problem where they had to solve for R between the planets because it involves scientific notation. Literally, about 20 out of 34 made a mistake with the scientific notation part. You need to be confident in this area. Okay, we did this earlier on in the year, and we also talked about how to use the calculator with it. So we've got our velocity, v, or speed. We have our omega. We're looking for lambda. Marilyn, sorry, you had a question. Go ahead.
Well, when you have like a negative exponent to the 10, move the decimal to the right, or is that like
When you get an answer, right, and you have a negative exponent, like 10 to the negative 2 or something, you might want to rewrite it. And then at that point, you can move the decimal. Just think when it's a negative exponent, the number's got to get smaller.
Is that the same thing as when you do like the 10 to the negative 6, like the square root of, like the 6th root of?
Yes and no. No, it's not. If you have r, some variable, to the 6th, then you take the 6th root to get r. Okay? But the scientific notation portion here just gets tacked on the end of the number. You're not solving for this. This is not a if this was a variable, you would take the 18th root, right? But it's not a variable here, so you're not going to be doing anything with those roots. Okay, what you're doing really here is just getting an answer, and then at the end we'll talk about how to rearrange that answer. So if I plug in my numbers now, or if I'm looking for, I should just solve algebraically. If I'm looking for lambda, I got to divide by omega. So let me divide by omega on both sides. So v over omega is equal to lambda. V, 3 times 10 to the 8. Omega, 3 times 10 to the 18. 3 divided by 3. Thank you. 1. Please don't put 0. I ask because I know it sounds ridiculous, but so many people cancel them and put a 0 there. It's not 0. 10 to the 8 over 10 to the 18. Very good. My units are meters because I know I'm looking for a length. Everything was standardized. Once I converted my units from megahertz to hertz, everything was then standardized, so I could leave it that way. Well, take a look. This here, if I were to write this as 10 to the negative 9, okay, I would recognize that, all right, what am I doing here? I'm taking this number and I'm going from a really even smaller number to a little bit of a bigger number. I know it sounds weird, but this number is bigger than this is. Because the negative exponent, works backwards. So something with a negative exponent, the bigger the exponent is, the smaller the number is. So this is now a bigger number. So this would be really just 0.1. Okay, so this is, Marilyn, kind of answering your question about how to move the decimal. So if I make this number a bigger number, this number has to become a smaller number then as a result to balance. Why did I use 10 to the negative 9? What prefix is 10 to the negative 9? What prefix was 10 to the negative 9? I just wrote it. What is it? Nano. Thank you. I'm glad you wrote it down or remembered either one. 0.1 nanometers. So it turns out that X-rays are insanely small. And that's what I was alluding to earlier. Okay, they're traveling literally through your body. They're actually traveling through your body. Okay, the same thing happens when there are nuclear disasters, when there's like a nuclear meltdown. A lot of these things emit gamma radiation that is very, very, very small wavelength, which is why it causes mutations, which is why people are still suffering today from things like the atomic bomb. That whole area, even like Chernobyl, where there was the meltdown, the nuclear reactor meltdown, it's still uninhabited. You see like wolves and like bears with literally like extra legs. It's not like, it sounds funny, but it's kind of freakish that these mutations are still occurring in that area because all of that radiation, it affected all of the crop life. It affected all of the plant life. And now these animals are eating things that have radiation poisoning in them. So there's been change over time to a lot of things. So it's really important that you understand that, yeah, people like to laugh about things, or not even laugh, but like talk about, nuclear war, like maybe it's no big deal, or you know what, the US has a lot of nuclear arms. We're all screwed if we enter nuclear war. No, seriously, we all are. You think like, we're in the US, we're safe, right? It's not the case, it really isn't. Because if somehow, someday, God forbid, this craziness continues, what's happening now, and we enter a war, you got to be really careful about this. It's not like right now, we're like, just because we're the strongest, it's not a big deal. Well, in the news recently, they've been talking a lot about other countries that are building up missiles, that are building up their nuclear warfare. You have to be concerned about that. It's not a small deal. This kind of stuff makes a big difference. We're talking about the nano level. It will affect crops. It will affect crop life. It will affect human life. So although maybe the earth won't explode as a result of this, good luck surviving when you have a nuclear fallout. That's why you see all those, like, I'm kind of like smiling now. It's not that this is funny, but like books and movies that have nuclear fallout, and like you look at what happens as a result, they're not exaggerating in these things. Crop life would cease to exist, or it would be all mutated, would not be able to be actual vegetation that we could use. So we have to consider this stuff. This is the wavelength of an X-ray. Nuclear stuff, even smaller. Gamma radiation, I think, is the smallest of your wavelengths. Mike?
No.
You sure? Okay. I kind of went off there for a little. Sorry. Let's go to the next topic. Let's talk about waves and energy for a minute. We used the snaky yesterday as an example, and I think it's a great example for this again. So I can quickly do it. You want to grab the others? All right. So if you take a quick look yesterday, if I don't put much energy into the wave, take a look, please. You got to see this, right? If I don't put much energy in, the wave amplitude is pretty small and it dies out pretty quick. But if I do this, we can see. Sorry, Martha. We can see. You even notice I said it? Oh, yeah, okay. You can physically see. Look, you give it more energy, the amplitude increases. So right off the bat, if we know that when we give it more energy, the amplitude increases, we could say that they're related directly. It turns out that energy is proportional to the square of the amplitude. Energy is proportional to the square of the amplitude. It makes sense of this for a minute. When we looked at that animation a little while ago, why did the waves sometimes continue forever? What did we turn off? Turned off friction. What does friction absorb or use up? Energy. So think about it. Now that friction's on, what happens to the amplitude suddenly? Yeah, it becomes zero almost, right? Look, here's positive amplitude the whole time. This has amplitude to it because I'm giving it energy. I'm the source, my hand. Well, I stop doing that, and what happens? The energy is absorbed by friction, so you can clearly see that energy and amplitude are related to one another. Okay, they're related to one another. Okay, and we could say that the other thing I wrote down was that a wave actually carries energy. It physically carries energy. So when you send a pulse, it carries it down the line. Hey, so listen real quick. Listen before you go anywhere. So at the very bottom of these notes, you'll see we talk about interference, and then some quick stuff at the end. I need you to watch it over break. We're a little bit behind the other class because yesterday was a C day. I'm trying to get through everything, but the time is just not there. So there's probably like 4 minutes left in the video that I recorded to go over these last few slides. So over break, over the next 5 days, you're doing that, and you're doing this homework, those two things. Okay, next week we have a lab. Is it exam? Yeah. Right now? Oh, yeah. All right. When it's exam. Every Thursday is exam. Grab a seat. Actually, yeah, give me a second. Perfect. Let's do this real quick. We'll get to exam. We will. I promise. I have extra minutes. I'm going to use it for teaching. So real quick, interference. Interference is important. Have you ever been listening to the radio and suddenly you hear static? Yeah. It's called interference. That's what it is. It's when waves counteract each other. So there's something called constructive interference and destructive interference. If two waves are pulsing toward one another and they both have positive amplitudes, they kind of combine with each other. When they're one positive and one negative, they kind of cancel each other out. So I'm going to talk quieter so it's not to teach you stuff. So I'm never doing this. So we will. I'll do a quick example. So the superposition principle, simply put, let me give you, it's really easy to show you. That's why I wanted to go back to this animation. It's a lot easier to show than it is to talk about. So the superposition principle is like this, okay? So if I were to, let's say this is, I want to loosen, I want to restart it. Restart, okay? I'm going to give it a pulse. I'm going to pause. Okay, now, watch what happens. If I send another pulse, I'm going to try and send another pulse to this. Hold on. I get this to come back. One more time. All right, ready? Okay, I'm going to send a pulse and pause. Okay, so it's tough to do this. But these two pulses were both moving left to right. And when they come together, look at what happens to the amplitude. What's happening to it? Yeah, it's getting bigger because both the pulses were moving on the positive side. And then they actually, look, they pass through each other. The waves continue. Then this one gets reversed on the bottom there. I'll explain that in a minute. But now watch what's going to happen is this. Now we have a positive wave over here. and a negative wave here. When they come together, what's going to happen there is they're going to cancel each other out and pass through each other again. So to just let you see a little bit better, I want to slow it down. Here. Let me restart it so you can see a little bit better again. Hold on. I didn't realize I could do slow motion. This is great. Okay. So I'm going to send another pulse when this one's coming back. I was too late. Damn. Try that again. Come on. Now it's like too slow. We can't wait for anything nowadays. I feel like I just have no patience anymore. All right. Look at the wave. See how it got taller? And then it got back to shorter. Now, the negative wave and the positive wave are about to come together. And when the negative and positive come together, they literally cancel each other out. And then it goes past each other. So the next slide you're seeing in your notes now, okay, this next slide right here, we're seeing that we have constructive and destructive interference. Well, when two waves come together, you literally just add them together. So if I have an amplitude here, let's say the amplitude of the first wave is like, I don't know, 4 centimeters, and this is 3 right here. Well, then this one will automatically be 7 centimeters. It's simply adding and subtracting. That's all you're doing with this. If this one has a positive 4 and this has a negative 3, then the answer would just be positive 1. So literally, the amplitudes are summed together. Read it as A, B, C, D, though. It's trying to show you the waves coming together, and then they pass through one another. Okay, but interference, there's a lot more to interference than this. This is just a primary theory about how wave interference works. Okay, the next slide talks about reflecting waves. And this is what you're seeing in that animation right here. So you can see the end. It could be a fixed end. And if I send a pulse on a fixed end, watch which way it comes back. Same wave, but it comes back on the opposite side. See how it's getting sent back on the bottom every time? Now, if I change that, end to a loose end, it's a little more obvious for this one. It makes sense of. So watch what happens. The rope gets slid up, which gives it potential energy. Well, then the rope wants to do what? It wants to come back down. When the rope comes back down, it's like me whipping on the sling or on the slinky. It sends back the same pulse. This end is fixed, so it's sending back the inverted. That side sends back the same pulse. Negative pulse, negative return. On a positive pulse, positive return. Yet this one is reflecting it. So what's happening here is that we notice that these waves on a loose end or a free boundary are simply reflected with the same wave on both spots. Whereas here, you have a positive amplitude. When it gets reflected by a fixed end, you get a negative amplitude. Okay, believe it or not, I know you're like, who the hell cares, right? Well, when are you going to see this? So think about things that are membranes. Anything that's a membrane or like a surface that has like a connection point at the end, the ends are fixed, and that's what you get. So if you were like smack on a membrane, it would start to vibrate up and down. Well, the pulses are going to reflect underneath. Whereas if something's connected to a free boundary, when there's a vibration, it will become like out of control. It'll move up, and then it'll slide right back down. So these are the two main types of waves that can be the main two types of ways a wave can be reflected. The last thing to quickly go over this. Okay, this is interference, but graphically. So if you think about interference as constructive or destructive interference, oops, I want to get rid of that actually. And we take a line. This is like the vertical line test, but it's not. Take a vertical line like the vertical line test and simply line it up anywhere. And what you're going to notice, what you'll notice is that one of these three waves, you know which one it is, it's red, is the result of the other two combined. And here's how we can see it. Take a look right here at this point. If I give values, call this 1 and 2, -1 and -2, I don't care about the x-axis. This value here of the height might be like 0.6. Well, this value here is -0.6. I'm looking at the y value. The x-coordinate is what? 1, 2, 3, so whatever that is. The y value here lines up with 0.6. Maybe this is around -0.6. When you add those numbers together, what should you get? And look at the resulting wave. Where is it? 0. So at any point in time, you can take a line and place that line on the graph. Depending upon where it is, it'll tell you which is the resultant wave. And you can test it out. Like, look right here where it is now. Well, I've got a positive wave, blue. It's about 0.2. Positive green, about 0.7. 0.7 and 0.2 gives me around 0.9. Pretty close to 1. So if you ever want to test it out, you could just say, you know what? What if you didn't know which was which? How could you figure it out? Well, just think about how it would work. If I were to take a look at this here and say, let's say, imagine the blue is the resultant wave. We want to make believe it is. It wouldn't make sense because this would be like 1.2, right above here, maybe 1.1. This would be like, I don't know, like 0.8. Well, 1.1 and 0.8 would give us 1.9. So the result should be up here. Yet it's here. So that means that the blue wave is not the result. So the sum of the two waves have to equal the third wave. And we're talking about the y values. The x values don't matter. The y values have to do with the actual amplitude, so you can see whether it's getting further amplified or, if it's getting, in this case, diminished or destructed. This is destructive interference right here. I mean, at this moment right here. Okay, whereas this is constructive interference. Okay, constructive is when we had the amplitudes were both positive and it became more positive. Destructive is when one was positive and one was negative and they kind of cancel each other out. Even if they're both negative, it's still considered constructive. So for an example like this one, let's go right here. Okay, if I take a look at this line right here now, I can see I've got, all right, this is like negative 0.2, it's like negative 0.6. Together that gives me negative 0.8. This is considered constructive interference also, but on the other side. Okay, please reflect on your day at some point. Okay? Please reflect on your day at some point. So all you have is homework over the weekend then, okay? If you want to start the problem set, you can do all the problem set now. 13:1 through 4. We're done with lessons. Lab next week, review, test. Lab, review, test.